In today's lecture, we will be exploring 5.5 and 5.6 with the double angle identities and the half angle identities. Sometimes they are called formulas. We will also be looking at product to sum formulas and sum to product formulas. First off, we want to start with the double angle formulas. So this is a variation of number 10 from page 236. The actual problem only asks us to find the sine of 2x and the cosine of 2x, but I added the tangent of 2x so that we could learn a little bit more. So what we would do here is we have two options. We can either go with the explanation in example 1 of 5.5, or we can go with the explanation that is presented in the video from MyOpenMath, and that would be for problem number 1. And I think the video explanation from MyOpenMath, problem number 1, is better than what the book is presenting because the book does not use triangles. And I think wherever you can use triangles, use triangles. So this is how I would say to do this problem. Start off by drawing the quadrant that you're in, and then put a triangle in that quadrant and label it. So here we know that tangent is positive and sine is negative. Tangent is positive and sine is negative only in the third quadrant. So the first thing we want to do is we want to draw a third quadrant angle. Next, we want to draw a triangle in that quadrant. And this triangle is going to correspond to x, all right? So this value right here that starts at the positive x-axis and goes all the way around, that angle is x. What do we know about x? Well, we know that the tangent of x is 5/3. Remember that tangent is opposite over adjacent for this reference triangle. So opposite over adjacent. But note that both the sine and the cosine values are negative. Both the x values and the y values are negative in the third quadrant. So what that means is we want to go ahead and add negative signs to both 3 and 5. So then next we need to have the hypotenuse of our right triangle. So 3 squared plus 5 squared is going to be 34. So that makes the hypotenuse square root 34. Okay, so the first step is done, and from here it should be pretty simple. So we're going to work through sine 2x, cosine 2x, and tangent 2x, starting with sine 2x. And then all we need to do is switch over to the formula. We see that the sine of 2x is 2 sine x cos x. So I write that on the board. 2 sine x cos x. And now I just replace sine x and cos x with whatever I get from the triangle. So the sine of x is negative 5 over root 34. And the cosine of x is negative 3 over root 34. And what's nice here is that the root 34 times root 34 is going to cause the denominator to be a rational number, so that's great. So then this simplifies. We have a negative times a negative, positive, 15 times 2, 30 over 34. And that further simplifies. I think I should do this up here. 30 over 34 simplifies to 15 over 17. Okay, so now we'll repeat this process again with cosine and with tangent. But as you can see, this problem is really not that bad once you get your triangle. All you got to do is set up a triangle and then fill in the values to the formulas. So a really simple formula sort of problem. But the key is just to remember that in the first place, set up your triangle. Okay, now the cosine of 2x actually has multiple formulas. So we can choose any one of these formulas. It doesn't matter. I think I'll go ahead and just pick the middle one arbitrarily, 2 cosine squared x minus 1. And if you're wondering why are there so many formulas, well, here's the original formula, cosine squared x minus sine squared x. And then these two are variations of cosine squared x minus sine squared x using the Pythagorean identity, right? So you can replace sine squared x in the Pythagorean identity with 1 minus cosine squared x, and that's how we end up with this second equation. And you can replace cosine squared x with 1 minus sine squared x, and that's how we end up with the third variation of the formula. Now, in the first place, you may be wondering, where do these angle formulas come from? Or maybe you're not wondering, but in any case, I'm going to tell you. These are from the sine sum and cosine sum and tangent sum formulas. So we learned that the sine of a plus b is going to be sine a cos b plus sine b cos a. Well, if a and b are the same value, if they're both x, then sine of x plus x is sine x cos x plus cos x sine x, which simplifies to here. So all I'm doing to derive these formulas is to replace a and b in the sine sum, cosine sum, and tangent sum formulas with x. Okay, so anyway, that's why there are 3 different options for cosine. Now we're going to also look at tangent. I'll go ahead and put that up on the board at the same time. Save me a little flipping back and forth. The tangent function has the formula 2 tan x over 1 minus tan squared x. And now I can flip back here. So I've put both of these up on the board. So now what I want to do is I want to simply replace cosine of x. Here's the square on the outside. I already know that the cosine of x is negative 3 over root 34. And then when I square that number, I end up with 9 over 34. That this further simplifies. You have 2 and 34 reduced, so that's 9 over 17 minus 17 over 17, which is negative 8 over 17. And it occurs to me that you probably can't see that. So there you go. Oh, and then the glare is there. Lovely. Anyway, that simplifies to negative 8 over 17, which I think you can mostly see there. All right, and now for this last part, we are going to replace tangent of x. And the tangent of x is already given to us as 5 over 3. So this results in a complex fraction. We have 10 over 3 all over, well, this is, let's see, 9 over 9, that's 1, minus 25 over 9. Maybe that was unnecessary because I'm about to clear the fractions anyway. Yeah, I could have just left this as a 1. Okay. I'm going to leave this as a 1 because I'm not going to combine those. Instead, I'm going to clear those little denominators. So I multiply the numerator and the denominator by 9 over 9. And that is going to then give me 30 over 9 minus 25, which is 30 over negative 16, or negative 15 over 8. Okay, so those are, this problem right here is going to correspond to number 9 in your homework, but for number 9, you don't have to do tangent of 2x. But on My Open Math, question number 1, you will find all 3, sine, cosine, and tangent are required. So as I was just saying, the previous problem I went over, number 10, will help you with question number 1 on My Open Math. Now question number 2 is a lot different. This is similar to questions 13 through 16 in 5.5 of your textbook. So I'm going to work through number 16 so you get an idea of how to do a problem like question number 2 or number 15. So here's question number 16. We're supposed to find sine of theta and the cosine of theta given cosine of 2 theta is equal to 2/3. Now this type of problem is only going to work if you know the cosine of 2 theta. And that is because cosine of 2 theta is unique in that it has 3 different formulas, unlike sine of 2 theta and tangent of 2 theta. And with those 3 different formulas, you are able then to isolate a single trig function, right? So let's look over at the formula again. We have, here we go. Cosine of 2x can equal any of these. And we need to find sine x by itself and cosine x by itself, or actually sine of theta, cosine of theta. So you can use either one of these or both of them. You wouldn't want to use the top one because you can't isolate a single trig function if you have both of them. So I will go ahead and use both of those. So let me put those on the board real quick. Okay, so what I've done here is I've rewritten the cosine 2 theta formulas that have only a single trig function. But instead of writing the version that says 2x, I've written 2 theta. So I've applied the formula specifically to this problem's variables. Now I'm going to replace cosine of 2 theta in each one of these equations with 2/3. Okay, so now what I want to do is I simply want to isolate cosine and sine. So I'll start by adding 1 to both sides and then dividing by 2. Right, so you had a 5/3 and divided by 2 is 5/6, and over here we're going to be subtracting 1. If you subtract 1 from 2/3, you get -1/3, and then divide -1/3 by -2, and you get +1/6. So while it's important that we have the parentheses around the 2 theta, because I have a product of 2 different numbers here, and I want to make it clear that both the 2 and the theta are inside cosine, the parentheses I was using here for theta were really unnecessary, and so I just went ahead and dropped them. Okay, so again, what I just did was I just did a reverse order of PEMDAS. I added 1 divided by 2. Here I subtracted 1 divided by -2. Now I've isolated cosine squared and sine squared. Now using the square root property, we're going to take the square root of both sides. And this is where we need to consider, are we going to have a plus or a minus for each of these? Okay, so typically when you take the square root of both sides, you have the plus and the minus. But let's consider, where is theta located? Theta is located between 90 and 180 degrees. So theta is in the second quadrant. In the second quadrant, cosine is negative, so we want to keep the -1. And in the second quadrant, sine is positive, so we would want to keep the positive version of that. And so here we have that cosine of theta is equal to -√5/6, but we want to rationalize that denominator. Multiply by √6/6. And so now we have that the cosine of theta is equal to -√30/6. And then over here, we would have that the sine of theta is equal to the positive 1 over 6, all in the square root. And then we want to rationalize the denominator, so then we end up with square root of 6 over 6 for sine of theta. Okay, that's number 16. Next, we're going to move on to verifying identities. Now remember that the point of homework is to prepare you for the quiz and the test and the final exam. Ultimately, to give you comprehensive mastery practice. So this is a version of question 3 from MyOpenMath. All of the versions of question 3 from MyOpenMath for this assignment look very similar. So the best thing for your understanding is if you go and attempt the version in your homework first before you see me do this, because you need the practice. So go and try this proof, verify this identity on your own first, and then watch me do it. Okay? So what are we going to do? We are going to replace sine of 2x with what sine of 2x is equal to. And that would be 2 sine x cos x. Now, for the denominator, we have 3 choices for cosine 2x. So we need to be strategic about which one we use. What we want to be able to do some sort of reducing, right? And if you want to be able to reduce a fraction, you need to either get the denominator so it can factor, or get the denominator so there's no longer any plus or minus signs. And if you think about cosine of 2x, let's just flip over to cosine of 2x. Oops, here we go. In each of these, there is the opportunity to isolate a single trig function, except for this one that's hanging around. So this one has a minus 1, and this one has a plus 1. Now let's go back to what's on the board here. I'm about to subtract whichever one I choose. And I'm going to have 1 minus whatever I replace. So what I would want to do is I would want to replace cosine of 2x with one of the versions of the formula that has a positive 1, so that I can have 1 minus 1, and that would cancel. So which of them is that? Which one has the positive 1? It's this last one here. 1 minus 2 sine squared x. So I'm going to replace right here. Cosine of 2x is going to get replaced with 1 minus 2 sine squared x. And then when I do that, and I use the distributive property, I can end up with then 2 sine x cos x over 1 minus 1 plus 2 sine squared x. And these will cancel, giving me 2 sine x cos x over 2 sine squared x. And now you can see that the 2's are going to cancel and the sine x's are going to cancel. Don't cross through your work. I want to be able to read it. So on any homework you ever submit to me, or any test material you ever submit to me in your handwritten work, if you cross through something, I will disregard it. So if you do a version of the problem and you mess up and you cross through it, I disregard it. But I will also disregard anything you cross out in your work that you intend to be there. So use check marks if you have to. So then this is going to leave me with a cosine x over a sine x. Now I've run out of space on this side, so I'll go ahead and just change what's on this side. 1 over tan x can be replaced with cotangent x, because they are reciprocal functions. And then I can replace cotangent x with cosine x over sine x. So you see that I have verified this identity. Okay, so next what I'm going to do is I'm going to do number 20 from the textbook. And I want you to try number 19 from the textbook first, or you can try number 20 and see me do number 20. But whatever you do, try either 19 or 20 before you watch me do number 20 so that you can have the practice before you see the answer. Because once you see the answer, you don't get real practice. So make sure you try 19 or 20, and that's on page 237 of your textbook. Okay, so here is 20. I'm going to work on both the left and the right hand side. So first of all, the sine of 4x is the same as the sine of 2 times 2x. Okay, this is not part of my proof. I'm just going to write this up on the board so you can visualize this. The sine of 4x is the same thing as the sine of 2 times 2x. So this is still going to qualify for the double angle formula, but instead of a theta, a 2 theta, I'm going to have a 2 times a 2x. So the 2x is going to replace the theta or the x in the formula, depending on what kind of formula you're looking at. Now the formulas I'm using happen to use x, which can be a little confusing. So it may be helpful to look at a formula that does not use x. But in either case, what we want to do is visualize this not as a 4 times x, but a 2 times 2x. What that allows us to do then is replace the sine of 4x with whatever it is that sine of 4x equals to by the double angle formula. So going back to the double angle formula, the sine of a double angle is 2 sine that angle cosine that angle. So for me, I'm going to write 2 sine 2x cosine 2x, because remember that 4x is twice 2x. Okay, so that's as far as I'm going to go on that side. Now I'm going to work on the left-hand side because I don't know how much further I would need to go or I want to go on this side. So I'm just going to work on this side and see what happens. I'm squaring a binomial, so I should get a trinomial, right? I end up with cosine squared 2x minus 2 sine 2x cosine 2x plus sine squared, okay, I ran out of space here, hold on, sine squared 2x. I guess I could have written it backwards. That would have been more strategic. Okay, so what I see here is I have a cosine squared and a sine squared together. And so I can replace cosine squared, sine squared with 1. So now I have 1 minus 2 sine 2x cosine 2x, which, hey, look at that! My left-hand side now equals my right-hand side. So I'm done with number 20. Here's number 46. Now, in math, a lot of discoveries are made through creativity. As a student, sometimes you also get to exercise creativity, but often what you get to do is learn tricks that other people have discovered. So, for number 46, we are going to use a trick. And you can keep this trick in your mind for future occurrences of the same kind of situation. And the situation is this. What if I need to fit something to a formula and it's kind of close, but not quite there? How can you force an expression to fit a formula? So what am I talking about? Well, let's look at this. I have a sine and a cosine being multiplied together. In my formulas, I see a sine and cosine being multiplied together, but there's a 2 out in front, not a 1/8. So it would be ideal if that 1/8 were a 2 and not a 1/8. Can I make a 1/8 into a 2? Yes, I could do that if I multiplied it by 16. But of course, I can't multiply it by 16 without also dividing by 16, because that would change the value. But that's exactly what we're going to do. The purpose of this problem is to simplify. So I'm going to multiply by 16 while also dividing by 16, and then I will not have changed the value at all, right? You're just multiplying by a version of 1. So now for my numerator, I conveniently have 2 sine 29.5 cosine 29.5, and this is still all over 16. So resist the urge here to reduce 2 and 16 back to 1/8, because that's where you came from. Keep your eye on the ball. Where are you going? You're trying to fit 2 sine 29.5 cosine 29.5 to one of the formulas. So it does exactly fit this formula right here. So now I can replace 2 sine 29.5 cosine 29.5 with sine of 2 times 29.5. So I replace the numerator now with sine of 2 times 29.5 degrees. And that then, of course, is what? 69? No, 59. Right. It's 30 and 30 is 60, so 59. So this is now the sine of 59 degrees all over 16. Sometimes you see this whole process done without the fraction underneath, but the fraction out in front. So you would see it as 1/16 times the sine of 59 degrees, and this would actually match the formatting of the original problem. So rather than having the 16 underneath throughout the work, you might see the 1/16 out in front with parentheses. Either way is fine. Okay, so that was 46. That was some simplifying work. And now we're going to do number 52. For number 52, we can express this as any trig function as long as it's in terms of x only, and we no longer have a 4x. So we can pick any one of the formulas that we have for cosine of 2x and do a replacement. Remember that this is the same thing as the cosine of 2 times 2x, so we're going to use one of the double angle formulas. It's going to be the most efficient if we pick one that doesn't have two different trig functions in it. It doesn't matter. I think I'll go ahead and pick 2 cosine squared x minus 1. No, actually, I think I like this one more. Let's do the bottom one. It really doesn't matter, but we'll do the bottom one. We'll do 1 minus 2 sine squared x. So this is 1 minus 2 sine squared x. But remember that my x in this problem is really 2x. Right? Okay, so I have replaced the formulas x with 2x, and now I have gone from a 4x expression to a 2x expression, but I need to go all the way to being simply in terms of x only. So now I got to replace sine of 2x with one of, well, there's only one formula for sine of 2x, and that formula is 2 sine x cos x. This whole sine of 2x is being squared. And now we can further simplify this. Remember always to follow PEMDAS. We're going to square before we multiply. And there we have it. This is not the only way to write the answer. In fact, the book has a different way of writing the exact same answer. It just depends on which formula you use to substitute it. So the book has for the answer 8 cosine to the 4th power of x minus 8 cosine squared x plus 1. Okay, now what I've done here is I've changed it to be in terms of x only, but it has just occurred to me that perhaps I need to go further because I need to get it to be as a single trig function of x. It's a little ambiguous, the directions here. So, assuming then that the directions really do want me to go to a single trig function and not have both a sine and a cosine, then what we would want to do is go back to a previous version of the cosine formula, one that involves just cosine, so we can keep doing cosine substitutions. So we can do that one too. That way you can see how we can arrive at this answer as well. Alright, so the other formula was 2 cosine squared x minus 1. But we're replacing our x here with 2x. So now we have 2 cosine squared of 2x. And remember, what goes here is going to be the formula for cosine of 2x of our choice. And we want one that's completely in terms of one trig function. So we can use, again, the 2 cosine squared. So 2 cosine squared x minus 1. And so now we are going to be squaring the binomial. And so we have 4 cosine to the 4th x minus 4 cosine squared x plus 1, and then we still have this minus 1 afterwards. And now this becomes 8 cosine to the 4th x minus 8 cosine squared x plus 2, and then we still have minus 1, and that's how we get to this answer right here. So that's how you get to a single trig function of x. Next problem. So now I've pulled up my open math, and here I have question 6, write the product as a sum. And those directions are really clear and also very suggestive. We need to turn a product into a sum. So you'll find in your textbook on page 235, product to sum identities. And this is what they look like. So I just need to identify what kind of product do I have. Well, I have the product of a cosine and a sine. So the product cosine sine and the product sine cosine, either one of these can be used. It really doesn't matter. It's kind of redundant to have both of them here. But anyway, we'll go ahead and use the cosine sine one here. So I'll write that up on the screen next to my open math problem. Okay, so here's my problem. Here's the formula I have chosen to use, the cosine u sine v. So my u, in this case, is going to be the 17p. And the v in this problem is going to be 8p. So the 8 is just going to stay out in front as I do this work. So here I'm going to go ahead and replace this formula with what I have here on this side. So the 8 is going to stay out in front. There's the 8. And now this part right here, the cosine 17p sine 8p, is going to be replaced now with this formula right here. So I have the 1/2 and let me just copy this again. Okay, so here is the formula. Here's the 8 out in front. Here's the 1/2 sine, etc. I'm going to replace every occurrence of u with what u is equal to here, and that is 17p. So here is 17p P, and here is 17P. And every occurrence of V, I get to replace with 8V. Sorry, 8P. 8P. So by the end of this course, you should be pretty good at formulas. 8 times 1/2 is, of course, 4. And this 4 is going to be out in front. And I have the sine of 17P plus 8P, which is, of course, 25P. And then I have minus the sine of 17P minus 8P, and that's going to be 9P. So even though they say as a sum, the sum is actually going to be a difference, and that's okay. But I'm going to have 4 sine 25P minus 4 sine of 9P. So 4 sine 25P minus 4 sine of 9P. Now let's see what this says here. 4 sine 25P minus 4 sine 9P. So that's how you do a problem like that. Okay, now let's scroll down to 8. Here we have a sum. It's okay if it's a difference, it's the same category. Sum as a product. So if we have a sum and we need to write it as a product, then we use the sum to product formulas. So in our particular problem here, we have a sine minus a sine. So I'm going to look for sine minus sine. You see there's sine plus sine, sine minus sine. I'm going to choose the sine minus sine. So I'm going to go ahead and write this formula now on my open math. Okay, so here is the formula, sine u minus sine v. We're going to replace every occurrence of u with 18.2v, and then we replace every occurrence of v in the formula with 2.6v. So then the result is going to be, I have the 2 here, and then I have the cosine, and now I'm going to replace u every time with 18.2. So 18.2 and then plus 2.6 is a total of what? 20.8v. So this is 20.8v because I'm adding the numbers together, and that's still all over 2. And then I have u minus v, so 18.2 minus 2.6 is going to be 15.6. So then I have a 15.6v all over 2. And then this number right here becomes a 10.4v. And then this one right here becomes a 7.8v. So we can see this answer now right here. We've got 2 cosine 10.4v sine 7.8v. I know I didn't show as much work on that one, but I'm wearing a wrist brace as it is from being online all the time. So I have to be somewhat reasonable about how much I kill my wrist. Alright, so let's look at question number 10. How would you do a problem like question number 10? Well, this is a cosine sum and a sine sum. And so you're going to want to do these using the sum to product formula of cosine sum and sine sum. So your numerator will be replaced by this part of the formula, the 2 cos cos. and the denominator will be replaced by this part of the formula, the 2 sine cos, and you'll end up possibly being able to cancel things. So let's go ahead and try that one this time on the whiteboard. Okay, so here we have the formula for cosine sum. It's 2 cosine u plus v over 2 cosine u minus v over 2. And then for sine sum, it's 2 sine u plus v over 2 cosine u plus v over 2. That's a little blurry. Let me bring this closer so you can see it. All right, there you go. Now, for our numerator and our denominator, we have a 2, which means that we can cancel the 2's. Also, the cosines of 9w minus 5w over 2 are identical, so we can also cancel those. That's going to leave us just with this cosine-sine combination. So these are going to cancel. These are going to cancel. And that's going to then leave me with the cosine of 9w plus 5w is 14w over 2, which is a 7w, over sine of 7w. And then that is the cotangent of 7w. So make sure you can get all that work done yourself in the same way. Okay, so this is a pretty long lecture as it is for 5.5, so I'm going to go ahead and do a second lecture for 5.6, so it's not going to be as large of a file. All right, so see you in the next part of the lecture.